All right, so today we're going to talk about the definite integral. And before we do that, I want to go briefly back to the previous lecture, and I want to just refresh your memory about these problems that we did in 11.1. So we had a couple different problems here. We had a car in which we were given some velocity data, and we were asked to estimate how far the car traveled, right? And we did that by um, estimating it using a left-hand sum and a right-hand sum. So we took these rectangular areas and added them up, and we based the height of these rectangles on, in the case of the green sum, these green intervals, we based the height of the interval on the left-hand data point, right? And so, for example, for the left-hand sum, the first interval is 2 time units wide and 20 units high. So we have a total of 40, I guess in this case, feet represented by that rectangle. Okay, and we just did that all the way along. We broke our time interval into 5 equal parts of 2 seconds each, and then base the height of the rectangle on the left data point. All right, so that's the left-hand sum. And then we had a right-hand sum. We did the same thing. We broke the time interval into 5 equal time units. Only this time we based the height of our rectangle on the right-hand data point. Okay, so you know that the actual area is somewhere in between the two. So we did the left-hand sum and the right-hand sum, got a lower estimate and an upper estimate, and then we can average the two to get a little better estimate. But there's a lot of uncertainty in it because we're using these wider intervals. Okay, and then we did another example where we did the same problem essentially, only we're sampling the velocity at a higher rate. So we've got velocity data for every second instead of every 2 seconds. Okay, so we can get a lot better estimate, right? So we did the left-hand sum and the right-hand sum in the same way, but you can see that the difference between the two is a lot smaller, and then we average the two to get the estimate. Okay, and so this, I briefly talked about how this is essentially the basis for the integral. So the idea is if you break the time interval up into finer and finer and finer slices, then you're going to get a better and better and better estimate. So so as the number of intervals goes to infinity, you get a nice smooth area that is the area under the curve. Okay, so let me go back to today's lecture, and so you can see here that we're defining the integral. Okay, we've got a new notation here. So we've got the integral, and we're using this new symbol here that's called the summa. Let me just, this is called the summa. You don't need to know the name. I just think it's interesting because it comes from the Latin word sum, right? And so it's a sum. Now here's the left hand and the right hand sums that we were just talking about. And if we take the time interval, well, in this case it's our x interval instead of time. We're just generalizing here. But if the x was time, then this would be a time interval. But we're generalizing it to whatever the x is, right? So so our interval that we're integrating over is from a to b, and we're slicing it up into an infinite number of slices that are each dx wide. Dx is our infinitesimal width. So you can see the relationship here between the integral and the sum. We have this when we're summing up discrete data points, like individual countable discrete data points, we use this Greek letter sigma to represent a sum, right? Sigma. And you can see we've got n data points, and we're summing it up. But now we're letting n go to infinity, okay? And when we do that, then we're using this new symbol called the summa. So it's basically the sum from A to B of the function times this infinite, I think is how you spell it. It's like this dx, or sorry, this delta x, right? The delta x corresponds with the dx. It's the infinitesimal difference in x, and instead of a sigma, we're using the summa to indicate a continuous sum instead of a discrete sum. Okay, so essentially that's how the integral is defined. We're finding the area under the curve, right? And we're basically taking the limit of either the right-hand sum or the left-hand sum as we slice that area into finer and finer increments, right? So, and these sums are called Riemann sums. F is the integrand, and A and B are the limits of integration. So, so I have another example here, and this is basically just showing you what that example in 11.1 showed you. That if you break your in this case again is time t. If you break your time interval into finer and finer slices, then you're going to get a better and better estimate of the area under the curve. So so to estimate, and this is just asking for the left-hand sum. So we have this bacteria population that's growing over a 20-hour period, okay, where t is the number of hours since the start of this 20-hour period. And we're given the rate at which the bacteria grows. So this is the rate. So this is the rate of bacteria growth in millions of bacteria per hour. Okay. And so if we want to find, we can actually just plug in these values of t and find the values of the function. So if we put in t equals 0, then we get 3. If we put in t equals 4, we get 16 times 0.1 is 1.6 plus 3 is 4.6, right? So we're just plugging in values for t to get a table of data. I'll just put in the values that I calculated. Okay, and they're just asking us to use the left-hand sum. So if we want the left-hand sum, we need to know. Okay, so we have so essentially n equals 5, right? Because we have 5 time intervals, right? 0 to 4, 4 to 8, 8 to 12, 12 to 16, and 16 to 20. So n equals 5, and our delta t is equal to 4, right? I guess that's what it says here. Yeah, all right, it says it there. So essentially we can get our left-hand sum by taking 3 times 4 plus 4.6 times 4 plus 9.4 times 4 plus 17.4 times 4, right? These are just the areas of those rectangles under the curve, plus 28.6 times 4. Now we don't want to include the last one because that's a right-hand data point in that interval. It's the value at 20, and in the interval from 16 to 20, that 43 is the right-hand data point. The left-hand data point is 28.6. Okay, so if we want the left-hand sum, we need the left-hand data point. Okay, so if we just add all of that up. Now, when I write this, I typically don't do it this way just because it's easier just to, I don't even have to write all of this out. I can just do 3 plus 4.6 plus 9.4 plus 17.3 plus 28.6, right? And then you can see how this 4 all factors out. So I can write this as 4 times 3 plus 4 plus 9.4 plus 17.4 plus 28.6. Oops, I missed one because that's only 4 data. Oh, no, it's supposed to be 4.6. That's why. All right. Okay, so when we do that, if I calculate that, we get 252 billion, not billion, it's in millions of bacteria. Hang on. Let's see if I can erase the B. Okay. All right, so million bacteria. Oops, bacteria. Okay. So notice that this is a rate, right? The original function was a rate, millions of bacteria per hour. But if we take millions of bacteria per hour times hours, we end up with millions of bacteria, right? Which is what we wanted to find, right? So in the last lecture, we were dealing mostly with velocity and distance. So if we take miles per hour times hours, we get miles, right? And then the same reasoning here. We take millions of bacteria per hour times hours, we're going to get millions of bacteria. Okay. Now this is just doing the same thing, finding the left-hand sum, only now we're breaking our interval into 10 increments, okay, of where the change in time is 2, right? The delta t is 2 for each interval. So again, I can just put these values into my equation and calculate what the function value is at each time, right? So 3.4, 4.6, 6.6, 9.4, 13, 17.4. Let's see, we got 22.6, 28.6, 35.4, and 43. Okay. So, but we really just asked to do the same thing. Only now our delta t is 2, and then we just want to add up all of these data values, right? So I'm not even going to write the whole thing, but okay, left-hand sum, so we got to stop at 35.4. Okay, and if I calculate that, I get 288 million bacteria. Okay, so that's going to be a better estimate. You can tell this is an increasing function. So if I have an increasing function, this function, since it's it's a parabola, I'm going to end up with something that looks like that, right? And so the left-hand sums are always going to be an underestimate, right? Because it's an increasing function. So these are both underestimates of the actual one. Now, if we wanted to be more accurate, we could do the right-hand sum and average them. But the point here was just to illustrate the fact that when you break it into finer and finer increments of time, then you're going to get a better estimate. Now, how do we write this? How do we write this as an integral? The way we write this as an integral, it's the integral, right? The summa from a to b. Okay, so we're trying to find the total area under the curve for the whole 20 hours. So it's going to be from 0 to 20, right? And the function, if I go back up here, you can see it a little better. If I can get them both on the screen. But it's 3 plus 0.1 t squared, okay? And then our infinitesimal dt, okay? So that's how we would write this as an integral, Okay, so that was just an exercise in actually writing it. Okay, let's see. There you go. Now I can see them both on the screen. Looks like I copied it correctly. All right, so that's how we write the integral. All right, so this next example is just tells you to estimate this integral. So if we want to, and we're given some data, all right, and there's no context here. I have no idea what this data is representing, but they want us to integrate this function, whatever it is. Okay, all we have is this data, so the best we can do is just compute the left-hand sum and the right-hand sum. So we're going to do that. Left-hand sum and the right-hand sum. Now in this case we have 6 data points, but we've got 5 intervals, right? We've got the interval from 5 to 10, 10 to 15, 15 to 20, 20 to 25, 25 to 30. So our n is equal to 5, and our delta t is equal to 5 as well, right? We're going in time increments of 5. I assume t is time. All right. So what I'm going to do for the left-hand sum, I'm just going to add up all the data points, the left-hand data points. 27 plus 30 plus 32. And then take it times our time interval, which is 5. And if I put that in my calculator, I get 640. That's my left-hand sum. And then the right-hand sum will just basically be the same sort of thing, except now I'm going to take all of the right-hand data points in each time interval. So in this interval between 5 and 10, I'm going to take the 23. Between 10 and 15, I'm going to take the 27. 32 plus 34. Okay, so there's my 5 increments, and the time interval for each increment is 5, and if I put that in my calculator, it's 730. Okay, and probably a better estimate then would just be to average the two. So if I compute the average, that's equal to, I'm just going to take 640 plus 730 all over 2. So I get 685. Okay, so that's as good as I can get with the data that I have. Because I really don't know what's happening between these points. All I have is data. I don't really have the function itself. Okay, so I'm just estimating the integral. Okay, now this is going to look kind of familiar too. Only now we're just using integral notation. All right, so we're given the function now as a graph instead of as data or even a function itself. So we're asked to find, but in each case the limits of integration are different, right? So here we're integrating from 0 to 2. So what this is asking is, what's the area under this curve f of x from 0 to 2, right? So I could block that off. So this first integral is really just asking, what is the area of that triangle, right? So it's 2 units wide, 40 units high. So I'm going to get 40. Okay. Right, because 1/2 base times height. Now another thing I could do, now I noticed like these, so the first one was from 0 to 2, but the next one is from 1 to 5. So from 1 to 5, right? And the next one is from 4 to 8. 4 to 8. And then 8 to 0, right? So what I could do is just like find the areas of each one of these slices and then add up the areas that I need to find my integral. So this area right here from 0 to 1, right? From 0 to 1, it's 1 unit wide and 20 units high, but it's a triangle, right? So this area is 10, 1/2 base times height. So here I could kind of actually block this off, right? Because I know this is 2 units high and 1 unit wide, so or 20 units high, 1 unit. So this represents 10. You can see that actually each rectangle, each one of these grid squares, it's not really a square in this case, but each one of these grid rectangles has a value of 10, right? Because it's 1 by 10. So this is 10, this is 10, and then this little triangle is half of 2 grid squares. So another way you could do it is just count up the little rectangles and multiply by 10. Would be another way you could find the area. So here the area between 1 and 2 is 30, so you can kind of see how it adds up. Here between 2 and 4, we've got 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, and then we have the 2 little half squares. So I use my mouse because, so you see what I mean. You're just gonna just count up the rectangles, and then I have 2 here that are half of 2 rectangles, right? So this is 10 and this is 10. But in all, I've got 120 for that whole area between 2 and 4. Now this one's pretty easy. I just count the rectangles, right? It goes all the way up to 80. So we have 1 by 80. So it's 80. And then this last one is 240. Okay. This is just there's a number of different ways you could approach this. But now that I've got all my areas found, I just need to pick the appropriate areas to add up. So when I integrate f of x from 1 to 5, I need to add the 30 in this first slice right here. I need to add that slice. I need to add that slice and that slice. The slice from 4 to 5. So I'm going to add 30 plus 120 plus 80, which gives me a total of 200 and, oops, 200. Okay. So again, 230. Okay. When I integrate from 4 to 8, I'm just going to add up the 80 and the 240. So that gives me a total of 320. So that's the area under the curve, under the f of x function, between t equals 4 and t equals 8. And then finally, the last one is we want just the whole area. So I can just add up 10 plus 30 plus 120 plus 80 plus 240. I can add up all the slices and I get 480. Okay, and that's the exact area in this particular case because we're not doing left-hand right-hand sums. You could do left-hand and right-hand sums, but this one you can find the actual area just using geometry. All right, now this next one I want to show you how to use your calculator. So I'm going to pause just a second to get things set up so I can show you the calculator. All right, so I've got my calculator here now, and I'm going to show you how you can calculate an integral with your calculator. Okay, so we're trying to find the integral from -1 to 2. Okay, so our limits of integration are from -1 to 3, and we want to find the integral under the curve x squared plus 2. Okay, so what you're going to do, turn my calculator on here. Let's clear all that stuff out. What I'm going to do is I'm going to go to the math key here. Now, I have a TI-84. I don't know what you have. I think a lot of people have TI-84, so I could show you on the TI-84. If you don't have a TI-84, I recommend just going to Google and typing in how to integrate on your calculator if you have that function on your calculator. So if you don't have that function on your calculator, I kind of assume that most people have something like this. I don't know if what's required for 108, but if you don't, just email me, let me know. All right, so I'm going to go to this math key. All right, I'm going to hit math, and then I'm going to scroll down to where it says f int, function integrate. All right, and I'm just going to hit enter. And look at that. It gives me the nice little integral. So I can just type in the integral that I want. So I want to go from -1. And then I'll go up here. I want to go to 3. And then I'm going to type in my function. So my x is here. I'm going to do x squared plus 2. Okay. There's my function. And then I have to tell it that I want to integrate with respect to x, right? So I'm just going to put an x in there. And that's it. So I just hit enter. Whoa, look at that. 17.33. 33333. 17 1/3. Okay, well, that's lovely. So there you go. Now I'm just kind of going to close this out and continue here. So I have to unplug the camera and plug in my tablet again. And I can get it to go in. There we go. Okay. Oops. All right, so we got 17.33 was our answer. That's all there is to it, really. 17.33. I'll just round it up to 2 decimal places. Okay? Easy as that. Oops. All right. So what else we got here? All right, the rest are practice problems. Okay. Now, see, that didn't take very long. 26 minutes. Ooh, that's good. So I will, I'll put the answers to the practice problems on Canvas in the completed notes. And then you have an exit ticket to do. So we will talk to you later.